Welcome to the first lesson in relativistic electrodynamics. So here we will prove that magnetism can be derived from electricity, electrostatics by using the relativistic relativistic principle, or electrodynamics plus relativity will lead to magnetism. So by the introduction of special theory of relativity, we have already seen that the many concepts of Newtonian mechanics were forced to be revised. Newtonian mechanics was not found to be inconsistent with the special theory of relativity. But classical electrodynamics is entirely different. Classical electrodynamics is already consistent with the special theory of relativity. We will see it in the future sessions. So here we will be expressing the existing rules of electrodynamics in a notation which is more relativistic in character. We are not going to change any existing laws of electrodynamics because already they are consistent with the special theory of relativity. In a sense, we can say that relativity is motivated from the classical electrodynamics. So the laws of electrodynamics will take a new form of symmetry from the point of view of relativity. Specifically, we will show that magnetism is a relativistic phenomenon of electrostatics. In particular, in this session, our aim is to calculate the magnetic force between a current carrying infinitely long wire and a moving charge, but without invoking the laws of magnetism. That is, we are not using the Biot-Savart law. We will be using the electrostatics plus relativistic formulation, and we will show that it will lead to another force called the magnetic force. So here we start from a reference system, yes. In that reference system there is an infinitely long straight wire which carries a string of positive charges and negative charges. These positive and negative charges are moving to the right and to the left with the same speed v in this frame. These charges are very close together so that we can define a continuous line charge density. It is lambda plus lambda for positive charge and minus lambda for negative charge. In this frame there is another point charge small q at a distance s from this conductor. It is moving towards the right with a speed u, and this speed u is less than v. So in this frame we see that the conductor is neutral because the conductor contains both positive and negative charges with the same linear charge density, so it is neutral. There is no electrostatic force between the point charge small q and the conductor, but there will be a magnetic force. And we will calculate that magnetic force but without invoking the laws of magnetism. So the important point is, in this S frame the conductor is neutral, it is carrying a current. Now what is the current here? Current is the current due to the positive charges is lambda v towards the right, and current due to the negative charge is again lambda v, it is again towards the right because negative charges moving to the left is equivalent to positive charge moving to the right. So the total current is 2 lambda v. Now we consider another frame S bar. The second frame is attached with the point charge small q. So the second frame is moving with a speed u with respect to the first frame. So in this frame the charge q is at rest and the positive charges inside the conductor will be moving towards the right, say with a velocity v plus, and negative charges is moving towards the left with a velocity v minus. Already we have taken that u is less than v. So as u is less than v, here the directions of positive and negative charges are not changed. They are moving towards the right and left, but their velocities will be different now. Now what is the velocity of the positive charge in the second frame? By using the transformation law of velocities in relativity, we see that Vx bar is equal to Vx minus u by 1 minus Vx u by c square, where Vx bar is the velocity of the object in the S bar frame, Vx is the velocity in the S frame, and u is the velocity of S bar with respect to S. Now applying this principle here, we see that the velocity of positive charges in the S bar frame V plus is equal to V minus U by 1 minus UV by C square. And velocity of the negative charge in the S bar frame is minus V. Here it is minus V because the negative charge is moving towards the left in the first frame. So it is minus V actually. So minus V minus U by 1 minus U into V becomes minus V. So it becomes 1 plus UV by C square. So the velocity of the negative charge is minus V minus U by 1 plus UV by C square. If we see the magnitude, it can also be written as V plus is V minus U by 1 minus UV by C square, and V minus is V plus U by 1 plus UV by C square. In magnitude, if we treat the magnitude, it can be taken as V plus U. So in textbook, you may see it is V plus U. There is no problem in calculation. We will be taking only V square. So whether it is direction or magnitude, there is no it doesn't matter, the result will be same. Now in S bar frame, the important point is this V plus and V minus are different. They are different in magnitude. Their magnitudes are not same. We see that V minus has more speed than V plus. As V minus is, the negative charges are moving with more speed than the positive charges. They are more contracted. There is Lorentz contraction. The contraction is more for the negative charges, or the negative charges becomes more close together than the positive charges. It means that the linear charge density of the negative charges, that is lambda minus, we can say lambda minus is equal to gamma minus into lambda 0, where lambda 0 is the linear charge density in the rest frame, and gamma minus is the ratio. Gamma minus is 1 by root of 1 minus V square by C square, where V is the V minus. That is the velocity of these negative charges in S bar frame. So due to the relative velocity between the S bar frame and the negative charges, the spacing between them is contracted, and therefore the negative charge in this S bar frame will have a linear charge density lambda minus is equal to minus of gamma minus lambda 0. This negative shows that the charge density is negative because the charges are negative, and this negative is just a notation for representing this gamma minus is the factor from the velocity of negative charges. Similarly, in this S bar frame, the positive charge will have a charge density lambda plus, which is equal to plus gamma plus lambda 0, where gamma plus is this one. And in this expression, there is a lambda 0. This lambda 0 is the linear charge density of the respective charges in their own rest frame. That is the important point. In their own rest frame means, now we have considered only two frames. The first frame is S frame, in which these two charges are moving with the velocity V. And the second frame is S bar frame. In that frame also these charges are moving with the velocity V plus and V minus. And lambda 0 is the charge density in a frame in which the charges are at rest. So it is not the same as lambda. Lambda is the charge density in S frame, because in S frame they are already moving with the speed V. So we can relate lambda with lambda 0 by lambda equal to gamma lambda 0, where lambda 0 is the charge density in their rest frame, and lambda is the charge density in a frame moving with a speed V, where gamma is 1 by root of 1 minus V square by C square. Now, by some algebra, we can show that gamma plus is gamma into 1 minus UV by C square into root of 1 minus U square by C square, and gamma minus is gamma into 1 plus UV by C square into 1 minus U square by C square. The proof is given in the last session. We can see it. Express gamma plus and gamma minus in terms of gamma. Here gamma plus is this one and gamma minus is this one. We take the denominator, root of 1 minus V square, V plus square by C square. It is root of 1 minus V plus is V minus U by 1 minus UV by C square all square by C square. So taking the LCM, 1 minus UV by C square all square minus V minus U square by C square by 1 minus UV by C square all square. take the denominator outside, it comes outside the root. It is 1 by root of u 1 minus uv by c square. Now expand this a minus b whole square, you will get this term a square plus b square minus 2ab, and this also by a minus b whole square, a square plus b square minus 2ab. So minus 2uv by c square and minus 2uv by c square gets cancelled. Remaining will be this one. This can be written as 1 minus u square by c square into 1 minus v square by c square. What is this root of 1 minus v square by c square? It is 1 by gamma. So it is 1 by gamma into this one. Therefore our gamma plus is 1 by root of this one. So the reciprocal of this one, it is gamma into 1 minus uv by c square by root of 1 minus u square by c square. Similarly, we can show that gamma minus is this one. Now going back, we see that gamma plus and gamma minus can be shown. And in this second frame S bar, so that conductor is negatively charged, because the negative charges are more close together than the positive charges. So the linear charge density, net linear charge density of the string in the second frame is lambda t is equal to lambda plus plus lambda minus, where lambda plus is gamma plus lambda 0 and lambda minus is minus gamma minus lambda 0. So lambda 0 into gamma plus minus gamma minus. Now what is lambda 0? Lambda 0 is lambda by gamma. Now we are converting this lambda 0 into lambda, that is into the S frame. So lambda by gamma into this gamma plus minus gamma minus is minus 2 gamma uv by c square into root of 1 minus u square by c square. So we see that gamma plus minus gamma minus is, it will be gamma plus plus gamma minus will be equal to, it is minus 2 uv by c square. This 1 and 1 gets cancelled. The remaining will be gamma into minus 2 uv by c square into root of, so minus 2 gamma uv by c square root of 1 minus u square by c square. So gamma and gamma gets cancelled. The remaining will be minus 2 lambda uv by c square root of 1 minus u square by c square. Now in the second frame S bar, due to the Lorentz contraction, the wire which is electrically neutral in the first frame is now charged in the second frame. Now the line charge lambda t, this lambda t sets up an electric field. It is an infinitely long wire, so electric field is 1 by 2 pi epsilon 0 lambda by s. So here lambda t by s. So it is the magnitude of electric field is, it is minus of lambda uv by pi epsilon 0 2, and this 2 gets cancelled, pi epsilon 0 c square s in the root of 1 minus u square by c square. So this force is the electrostatic force between the point charge q, it is at rest in the S bar frame, and the charged conductor. Now the conductor is charged. Now in the S bar frame, the force is electrostatics. Now there is an electric force F is equal to QE, that is equal to minus lambda u by pi epsilon 0 c square s into QU divided by root of 1 minus u square by c square. We just multiply this one with the q and just a rearrangement. Now if there is a force in S bar frame, there should be a force in S frame by the special theory of relativity. By using the relativistic principle, we can transform this force, that is F bar in the S bar frame, to the force F in S frame. So the transformation equation is F is equal to root of 1 minus u square by c square in F bar. So it becomes minus of lambda v qu by pi epsilon 0 c square s. Just it will cancel the root of 1 minus u square by c square in the denominator. Now this force can be written in a more familiar form. It is minus qu into lambda v by pi epsilon 0 c square. Now what is c square is 1 by root of mu 0 epsilon 0. And our lambda v, it is the current in the conductor in the first frame S, that is 2 lambda v. So lambda v is I by 2. So in terms of this, we can see it is minus qu into lambda v is I by 2, and epsilon 0 c square is mu 0, so mu 0 I by 2 pi s. So it is equal to minus q u b. What is this mu 0 I by 2 pi s? Mu 0 I by 2 pi s is the magnetic field produced by an infinitely long straight wire carrying a current I, and q u b is the magnetic force experienced by the point charge q moving with a speed u in a magnetic field b. So what we have obtained is the magnetic force between the point charge q and the infinitely long wire carrying a current I. So we have obtained the Lorentz force law in the system S, but without invoking Biot-Savart law. So the net is in the frame S bar, the charge Q is attracted towards the wire by purely electrostatic force, because in this frame the charge Q is at rest and the conductor is charged. It is negatively charged. But in the frame S, the charge is attracted towards the wire by purely non-electrical force, because in the S frame the conductor is neutral. So what is this non-electrical force? That non-electrical force is the magnetic force. So electrostatics and relativity imply the existence of another force. This other force is called the magnetic force. Electrostatics means in the S bar frame it is the electrostatic force. If we transform that electrostatic force into the S frame by using the principle of relativity, this transformation equation is the principle of relativity. By using that principle of relativity, we obtained the force experienced by the charged particle in the frame S. So that happens to be equal to the Biot-Savart, the Lorentz force law. So electrostatics and relativity imply the existence of another force, and this other force is the magnetic force. So we can see that magnetism is a relativistic phenomenon of electrostatics. So thank you for watching.